How many sides does a circle have? 2, inside and outside. We're actually going to be looking at the inside and outside of triangles, and by coincidence, some circles might show up. And in particular, we're looking at special triangle segments. The first part we're looking at are the perpendicular bisectors. As you may recall, a perpendicular bisector goes through the midpoint of a segment. And the cool thing about it is that any point on that segment is equidistant. Any point on that bisector is equidistant from the endpoints of the segment that it's bisecting. So if I was going to do the congruence statement, I could say that this length here, AD, is going to be the same as DB. So AD and BD are congruent. C, this one is a little easier because C is the midpoint, so it's pretty obvious that AC and BC are also congruent. Now we're going to take a look and actually create some perpendicular bisectors. This is Geogebra, and if you notice here, I can select the option to do a midpoint. So one of the things I'm going to do is I'm going to mark a midpoint or center on each of these sides. So I just have the midpoint tool, click, and even if I'm on the edge, it still finds the midpoint, which is pretty cool. Then the next thing I want to do is create a perpendicular line. So I click on the line I'm interested in, and then the point. Click on the line I'm interested in, and the point. Here's the line and the point. So I've created perpendicular bisectors because I marked all the midpoints and did perpendicular lines. So where do the perpendicular bisectors meet? In this instance, this is a 90-degree triangle, and you can see that the bisectors are meeting on the hypotenuse. In fact, they're meeting on the midpoint of the hypotenuse. Why does that make sense? Well, if you look at this bisector right here, it's going to be going halfway between this first point and the second point. And it's making a right angle. This bisector is making a right angle, and remember I have 90 degrees here. So it makes sense that they meet, that they've made the same length. This length here is the same as this and this. This length here is the same as this length right here and this top one. So I have two congruent triangles, which means that these two lengths will be the same and they meet at the midpoint. Well, that's pretty cool. So the perpendicular bisectors for a right triangle are going to meet at the midpoint of the hypotenuse. But what if the triangle were acute? So I'll just move this around, and you can see that the points where they meet, and I have a cool way of marking that, and click two segments, and it shows you where they intersect. So the midpoints where these meet are inside the triangle when my triangle's acute. If I go greater than 90 degrees, then the point of intersection moves outside of the triangle. So, since this point is equidistant from the three vertices, you can actually make a circle. So when we had the acute triangle, there's that little intersection. This point is equidistant from A and B, and it's also, because it's on this perpendicular bisector, it's equidistant from C to B. Since the distance to A, B, and C are the same, that is the center of my circle that goes through A, B, and C. And this also holds, whether it's a right triangle or an obtuse triangle. The only difference is that center is either going to be inside the triangle, on the edge of the triangle at the midpoint there, or outside of the triangle. So again, intersection for acute is inside the triangle. For the right triangle, it's on the hypotenuse, on the midpoint. And for an obtuse, it is outside of the triangle. Now, you're not really going to be doing a lot of, you're not going to be doing any circles through any points, but one thing you will be doing is using the properties of the bisectors to solve problems. One thing to keep in mind is that it divides it into two congruent segments. So you're probably going to set up an equation where each half of the segment is equal to each other. All right, so you can say this piece is equal to that piece. Another interesting thing is that they also create right triangles. So you may be able to use the Pythagorean theorem to solve for a length when you are looking for a leg and you know a hypotenuse or vice versa. So in this example, DE is a perpendicular bisector of AC, and we're going to find AC, DE, AE, and AD, which is a lot to find, I know. So We know it's a perpendicular bisector. That tells me that AE and EC are congruent. So I can set those two values equal. Then I'm going to solve algebraically, first subtracting 3x from both sides, and then adding 7 to both sides. And I get 8 equals 2x, or x is 4. So the first thing I'm going to do, it says find AC, but let me go ahead and find AE first. So I'll substitute in the 4, and I find out that AE is 13. Well, since these two segments here, the AE and EC, are congruent, I know that EC is also 13, which makes it pretty easy to find AC, the total. It's just going to be the sum of those two, or 26. I'm also can find DE. I know that it's 2x plus 1, and I substitute in again the 4 from here in, and I get 2 times 4 plus 1. 8 plus 1 are 9. So that side is 9. Finding AD, well, I see a right triangle formed here. So I'm going to use the Pythagorean theorem. So let's go ahead and clear that up. And I have 9 and 13 in this right triangle, and I'm trying to find AD. So I know AD squared is 13 squared plus 9 squared, or 169 plus 81, which is 250. But this length isn't 250. I need to take the square root of both sides. So AD is the square root of 250. So this would be your answer for the length. But if you're trying to simplify the radical, which will be come in more handy when we do the special right triangles in the February time frame, or also in Algebra 2, let's go ahead and practice that. So what you do is you look for a perfect square that's a factor, and I know 25 is 5 squared. So I factor out the 25 from 250, which is, so it's going to be 25 times 10. Well, square root of 25 I know is 5. So my simplified answer is 5 square root of 10. So for further reflection, do you need to draw all 3 perpendicular bisectors to find where they intersect? You might have noticed when I was using Geogebra that you could actually see where the 2 of them intersected, the third one also hit. So you actually only needed to draw 2 of the bisectors. And why do you think the type of triangle influences where the perpendicular bisectors meet?